Have you heard about performance review or performance evaluation as it is commonly called? Most organizations today conduct performance review to ensure the mutual needs of the employee and organization are met. Do you know what is the process or system employed to measure employees' performances? Are you aware of the parameters managers use to assess performance level of the employees? Well, the managers use different parameters such as the work quality, punctuality, attitude, client feedback, and many more to check employee efficiency at work. Just like these work performance parameters, the performance of transmission line is also measured using different parameters called the parameters of line. In this module, you will be introduced to different parameters of transmission line. You will see how conductors used for power transmission creates different effects in transmission lines. In addition, you will also touch base upon an advanced feature of conductors, transposition. Throughout the module, I will share different diagrams and videos to help you better understand the concept of transmission lines. Do look out for these. Let's get started. By the end of this module, you will be able to explain different parameters of transmission line, define the skin effect, summarize the causes and factors affecting skin effect, define the proximity effect, compare the two cases of proximity effect, summarize the factors affecting the proximity effect, define the Ferranti effect, summarize the causes of the Ferranti effect, illustrate transposition of conductors, explain the need, method, and disadvantages of transposition. To develop models of transmission lines, we first need to determine the transmission line parameters. These parameters, known as the parameters of the line, tell us about the performance of transmission line. These parameters are uniformly distributed along the line. Hence, it is also called the distributed parameter of the transmission line. Transmission line parameters can be classified into four categories: line resistance, line inductance, line capacitance, and shunt conductance. The line inductance and line resistance form series impedance, whereas the line capacitance and shunt conductance form the shunt admittance. Click the tabs to learn more about these parameters. Line resistance is a measure of the opposition to current flow in an electrical circuit. The conductors of the transmission lines have small resistance. For short lines, resistance plays an important role. As the line current increases, so does the ohmic loss, I square loss. The resistance R of a conductor of length L and cross-section A is given by the formula R is equal to rho multiplied by L and divided by A. The current flow in the transmission line induces the magnetic flux. When the current in the transmission line changes, the magnetic flux also varies, due to which electromotive force EMF induces in the circuit. The magnitude of induced EMF depends on the rate of change of flux. EMF produces in the transmission line resists the flow of current in the conductor, and this parameter is known as the inductance of the line. In the transmission line, air acts as a dielectric medium. This dielectric medium constitutes the capacitor between the conductors, which store the electrical energy or increase the capacitance of the line. The capacitance of the conductor is defined as the amount of charge per unit of potential difference. Capacitance is negligible in short transmission lines, whereas in long transmission line, it is the most important parameter. It affects the efficiency, voltage regulation, power factor, and stability of the system. Shunt conductance is due to the flow of leakage currents between the conductors separated by insulating medium. It is distributed uniformly along the whole length of the line. Represented by the symbol Y, it is measured in Siemens. Do you know how a conductor used in transmission lines carries direct current and alternating current? Do you see any difference in the flow of current density in these two different scenarios? Can you tell me what happens when the conductor used in transmission lines carries the electric current flow mainly at the outer surface or the skin of the conductor? Well, the answers to these questions lie in the concept of the skin effect. What is skin effect? Let's learn further. The phenomenon of unequal distribution of current over the entire cross-section of the conductor being used for long-distance power transmission is referred as the skin effect in transmission lines. This effect is negligible in case of a very short line, but with increase in the effective length of the conductors, skin effect increases considerably. Click the play button to view a video that explains in detail some other phenomenon of skin effect. For understanding the reason of skin effect, carefully observe the given figure. In the figure, I is the AC current flowing in the conductor. This current I create a circular magnetic field H shown in blue as per the right-hand thumb rule. The induced magnetic field in turn finds a way to discharge the stored energy in form of current IW. In other words, the magnetic field induces a current in the circular loop of the conductor. This backward current resists original flow of current, due to which the flow of AC current reduces reasonably at the center. This effect is known as skin effect. Cross-sectional area of a round conductor available for conducting DC current, DC resistance. Cross-sectional area of the same conductor available for conducting low-frequency AC, AC resistance. Cross-sectional area of the same conductor available for conducting high-frequency AC, AC resistance. So now you know that skin effect is caused due to alternating current flow and not because of direct current flow. Now let us look at the factors affecting skin effect. Click each factor to learn more. Skin effect is more in the solid conductor and less in the stranded conductor because the surface area of the solid conductor is more. Skin effect increase with the increase in the permeability of the material. Permeability is the ability of material to support the formation of the magnetic field. Skin effect increases with the increase in diameter of the conductor. Skin effect increases with the increase in supply frequency. Along with the skin effect, another effect known as proximity effect is a common problem found in most conductors used in transmission lines. So, what is proximity effect? Proximity effect is the tendency for current to flow in other undesirable patterns, loops, or concentrated distributions due to the presence of magnetic fields generated by nearby conductors. Take a look at two different cases to better understand the concept of proximity effect. Click each case to learn more. Of the halves of the conductors which are close to each other cancel each other and hence no current flows through that halves portion of the conductor. The current is crowded in the remote half portion of the conductor. When the conductors carry the current in the opposite direction, then the closed part of the conductor carries more current and the magnetic field of the far off half of the conductor cancel each other. Thus, the current is zero in the remote half of the conductor and crowded at the nearer part of the conductor. Now, let us look at the factors affecting proximity effect. Click each factor to learn more. The proximity effect increases with the increase in the frequency. The proximity effect increases with the increase in the diameter of the conductor. Proximity effect is more on the solid conductor as compared to the stranded conductor, that is ASCR, because the surface area of the stranded conductor is smaller than the solid conductor. If the material is made up of high ferromagnetic material, then the proximity effect is more on their surface. Do you know what type of effect is created when the voltage at the receiving end of the transmission line is more than the sending voltage? Well, such effect is known as the Ferranti effect. Upon disconnection of many loads connected at the receiving end, the voltage at the receiving end, VR, of the transmission line becomes higher than the sending voltage, Vs. The effect in which the voltage at the receiving end of the transmission line is more than the sending voltage is known as the Ferranti effect. Such type of effect mainly occurs because of light load or open circuit at the receiving end. Ferranti effect is due to the charging current of the line. Click the play button to learn more about the Ferranti effect through a phasor diagram. When an alternating voltage is applied, the current that flows into the capacitor is called charging current. A charging current is also known as capacitive current. The charging current increases in the line when the receiving end voltage of the line is larger than the sending end. In the figure, VR is receiving end voltage, Vs is sending end voltage, C is line capacitance, X is line inductance, R is line resistance, Is is sending end current, IR is receiving end current. It is seen from phasor diagram that OE is greater than OG. In other words, the voltage at the receiving end is greater than the voltage at the sending end when the line is at no load. Such effect is known as the Ferranti effect. Generally, this sort of effect happens due to an open circuit, light load at the collecting end, or charging current of the transmission line. Ferranti effect happens only for long lightly loaded or open-circuited energized lines. It mainly occurs due to the light load couples with the line capacitance and charging current. Take a look at the graphic below that further elaborates the causes of Ferranti effect. Click each factor to learn more. Ferranti effect depends on an open circuit and light load at the collecting end. In line capacitance, or charging current, cables have more capacitance than bare conductor per length, whereas in line length, long lines have higher capacitance than short lines. Charging current turns more important as load current decreases and it increases with the voltage of the system given the similar capacitive charge. You have learnt how conductors used for power transmission carry current in varied directions, causing different effects. Do you know about one of the advanced features of conductors, transposition? Transposition of conductors refers to the exchanging of position of conductors of a three-phase system along the transmission distance in such a manner that each conductor occupies the original position of every other conductor over an equal distance. Let's look at some of the characteristics of transposition. The transposition is a physical rotation of the conductors so that the conductor is moved to take up the next physical position in the regular sequence. The transposition of the conductor minimizes and also equalizes the mutual inductance between the transmission lines. The irregular spacing between the conductor gives a complex value of inductances, which makes the study of the power system complex. The transposition is mainly done in the switching station and the substations. Now, look at the figure to see how the three-phase lines are transposed every 1/3 of the length, thus limiting the effect of mutual inductance. Are you equipped with the following questions popping up in your mind? Why do we need transposition? What is the method of doing transposition? Are there any disadvantages associated with transposition? Click the tabs to find answers to the above questions. The inductance of unsymmetrical line causes voltage drops even if the voltage is in a balanced condition. Because of the inducing voltages, the magnetic field exists in the conductor, which causes the interference in the line. This can be reduced by continually exchanging the position of the conductor, which can be done by transposition of the conductors. The transposition of the lines can be done by placing the 1/3 segment of all three phases of the conductor in the same line. The transposition balances the capacitance of the line, due to which the voltage is also balanced. Frequently changing the position of conductors weakens the supportive structure, which increases the cost of the system. In this module, you learned about different parameters of transmission line, line resistance, line inductance, line capacitance, and shunt conductance. Determining these parameters are important to develop models of transmission lines. The line resistance and line inductance form series impedance, whereas the line capacitance and shunt conductance form the shunt admittance. Different effects in transmission line: skin effect, proximity effect, and Ferranti effect. In skin effect, the current flow mainly occurs at the outer surface of the conductor. In proximity effect, current flows in undesirable patterns due to the presence of magnetic fields generated by nearby conductors. In Ferranti effect, voltage at the receiving end of the transmission line is more than the sending voltage. Causes and factors affecting skin, proximity, and Ferranti effect. Transposition of conductors. Need, method, and disadvantage of transposition. Transposition helps the conductor to equalize the mutual inductance and capacitance between the lines. Click on the PDF icon to download the